Okay, Algebra 1 fans, our topic for today, we're going to start Unit 9, 9-1, Graph Quadratic Functions. And after this lesson, the things that we should be able to do, know how to do graph quadratic functions, analyze the graphs, talking about properties and things, find the maximum, minimum value of a quadratic function. So before we start, let me give you your joke of the day. I'm reading a book about anti-gravity. It's impossible to put down. Okay, if you get that, hopefully, gravity, up and down. It's actually a really appropriate joke because when we talk about quadratic functions, here's the shape. So you have this curved shape here. This one's going down, it turns and then comes back up. This one goes up, it turns and it comes back down. And these shapes are what we call a parabola. So these two types of curves are called a parabola. And some aspects of this, some properties, when you have a quadratic function, you'll notice that in this case it's a bottom point. That's the lowest point. That is called the vertex, or what we call a minimum. Minimum is the lowest. Now this one, since the parabola goes up, the vertex is the highest point, so we call that a maximum. So parabola, there's this bowl shape. If you think of a bowl, where you're putting cereal in or something, this kind of takes that shape and it can open up or it can open down. And we'll talk in a little bit about how that happens. Now, another property of quadratic functions, is that through the vertex, if you draw a vertical line, that is called an axis of symmetry. Axis, if you think of x-axis, y-axis, it's a line. Okay, so an axis of symmetry is a line, and if something is symmetrical, it means that we can fold one side of it and it folds onto the other side. Okay, so if we take the left side and we fold it across this line, it'll match. It'll fold onto the right side. So a parabola, a quadratic function, is symmetric. Now there are a lot of applications to this. So what objects have the shape of a parabola? Well, first of all, this one here that is going up, but it's actually opening downward. If you throw something in the air, it takes this path, it goes up, but then eventually it hits a maximum and then it comes back down. Anything that you throw into the air is eventually going to come back down because of the rules of gravity. So when you talk about projectile motion, throwing something, shooting something, firing something into the air, it's going to take this parabolic path. But there are other things that have this kind of shape. If you think of headlights of a car, headlights are not flat. If you look at the headlights, you'll see that they're curved outward because that maximizes the amount of light that can be shown. And then another thing that you're familiar with would be a satellite dish. So when you see the shape, when you see a satellite, it has this parabolic shape to it. And the reason is, another piece of a parabola is there's a point, a fixed point here, where this point is equidistant to the other points on the parabola. So there's this point. If you take a satellite, for example, what a satellite is doing is it picks up a radio wave or a television wave, something like that. And where it hits the dish, it's going to bounce and reflect to this point right here. No matter where it hits, because the shape is parabolic, it's always going to hit, it's going to reflect and bounce to this one point here. And so that's another property of a parabola. So the reason satellite dishes are parabolic is because they pick up those waves and then they put them into this one point right here. So anyway, there's a lot of application to parabolas, and we'll get into some of those. So the equation of a quadratic function, f of x, that's the same thing as y equals ax squared plus bx plus c. So we've been factoring these, we've been talking about quadratics, and now we're going to actually look at them. What do they look like? What kind of properties do they have? Where can we use them? The x squared term is what we call the quadratic term. because the exponent is a 2. The middle term here is called the linear term. So if you think of y equals mx plus b, this is x to the first, that's the linear term, and then the c is what we call the constant. That's the number without the variable, the number by itself. So let's graph one of these. Let's take a look at it. So number 1, graph f of x equals x squared plus 2x minus 3. Now one way that you can always graph is you can make a table of points. You can pick x values, because when you substitute an x value into a function, you always get a y value. So let's say we take negative 3. So on the side here, I'm going to write this down. We're going to take negative 3 squared plus 2 times x, which is negative 3, and whoop, that's minus 3. Okay, so here's the function, x squared plus 2x minus 3. All we're doing is substituting negative 3 for x. And remember that the x values are what we call the domain, and the y values are what we call the range. Okay, now if we work this out, when you square a negative, you get a positive, that's 9. 2 times negative 3 is minus 6, and minus 3. 9 minus 6 is 3, minus 3 is 0. So the y value is 0. When x is equal to negative 3, y is equal to 0. All right, let's take another one. Negative 2 for x. So again, we have x squared plus 2x minus 3, but instead of the letter x, we're going to substitute the number negative 2 this time. So this is going to be negative 2 squared is 4. Plus 2 times negative 2, that's minus 4, and subtract 3. 4 minus 4 is 0, minus 3 is negative 3. Okay, let's take negative 1. And I'm just going to go down here. So x squared plus 2x minus 3, we're going to substitute the negative 1, and this will be 1. This will be minus 2, minus 3, and 1 minus 2 is negative 1, minus 3 is negative 4. Now, we always want to substitute 0. 0 is the easiest number to plug in because 0 squared, anything times 0 is always 0. So 0 squared is 0, 2 times 0 is 0, minus 3, and we get negative 3. And if we substitute 1, so x squared plus 2x minus 3, notice how I'm using parentheses here every time? And then I'm just substituting my number. 1, 1, 1 squared is 1, 2 times 1 is 2, subtract 3, 1 plus 2 is 3, minus 3 is 0. All right, so what does this look like? Well, let's plot the points. Negative 3, comma 0 is on the x-axis. Negative 2, negative 3 is left 2, down 3. Negative 1, negative 4, left 1, down 4. 0, negative 3 is on the y-axis. And then 1, comma 0 is, again, on the x-axis. So what you see here, here's that parabola shape. Here's that curve. If we kept going, so let's say we put 2 in. If we work that out, we would get 2, comma 5. And so we get this shape. I'm going to draw this. And one of the neat things that we can do, since we know something about parabolas, we know that they are symmetric to this axis of symmetry, to this line. Well, the line goes through the vertex, and looking at this, it seems like the vertex is right here at negative 1, negative 4. So I'm going to draw a dotted line here. Here's our vertex. And if you look at the points, so for example, these 2 points, notice how they're each 1 space from the line of symmetry. Notice that these 2 points are 2 spaces from the line of symmetry. Now this point here is 3 spaces, so if I went 3 spaces on the other side, I'll do that in blue, notice that that would continue our pathway right there. Okay, so you can also get points if you know the line of symmetry, the axis of symmetry where the vertex is, you can get more points if you need it. All right, so here's our shape here. Now let's talk domain, range, intercepts, vertex. The domain is all the x values. Now we actually have 7 points here that we've graphed, but notice because we connect these, the function is not just these 7 x values, it's more than that. From left to right, this arrow means you're going to keep going to the left. You're going to keep going to the right. So if I plug -6 in for x, I would get a y value somewhere up here. If I plugged in +5 for y, we would get a y value up here. So what's happening is that the domain is what we call all real numbers. All real numbers. The symbol for that is a double bar R. You could write it that way. The other way that we're going to write it, I'm going to introduce a notation here. We can say -infinity is less than x is less than +infinity. Our x values are from -infinity to +infinity. In other words, we keep going to the left and we keep going to the right. So all the real numbers. So the easy way, I think, would just be all real numbers. Now the range is not all real numbers. The range is the y values from lowest to highest. We actually have a lowest value right here. We have our vertex. In this case, that is what we call the minimum, the lowest. Now the y value is -4. Now then, everything goes up. Every single y value is going to have a point on the function. Every single y value will have an x value. Every single y value will have an x value. Even if I keep going up, eventually we'll have a point on this graph. So all the y values that are greater than or equal to -4 will have an x value. So they'll exist in the function. Now if I try -5, oh, there's no point where the y value is -5. So that's not part of the range. So the way we're going to write this, you can say all real numbers, I'll give the symbol, greater than or equal to -4. All real numbers greater than or equal to -4. Now, if I wanted to write it as an inequality, I would say -4 less than or equal to y less than infinity. I have to put the less than or equal to part. I have to put the equal to part because this number -4 is part of the range. -4 is part of the range, so I have to include it. Now, for infinity, infinity is a concept. It's actually not a number. So infinity, positive infinity, means you keep going up. You're never going to stop going up. But since it's not a real number, then we don't put the equal to part for that. Okay, the last couple properties here, the x-intercept is where we cross the x-axis. Well, we've got 2 of those. So we have an x-intercept at -3, 0, and then an x-intercept at 1, 0. Okay, so let me label that. Those are the x-intercepts. The y-intercept is where we touch the y-axis. So here's the y-axis. Right here is the y-intercept. And that's at 0, -3. Because we don't move left or right, so the x value is 0. And then the vertex is here. That was -1, -4. Now, if we wanted to, we could also say the axis of symmetry, that was the vertical line that goes through the vertex. Now, a vertical line is x equals a number, and that x value is -1. So that would be the equation x equals -1, and that is the end of part 1.